So we're going to talk today just about one little piece of something called Descartes' rule of signs. And so we'll just look at what Descartes' rule of signs will do for us.
Word. I'm scared.
Yes, Descartes is a French man. René Descartes.
Both cards.
And we'll end up with some time today where you can ask questions from the homework assignment. You can work on your homework assignment for tonight. We're kind of wrapping up chapter 4 so we can kind of get into those things that we have questions about. Okay, so Descartes' rule of signs will tell you how many possible positive real zeros and how many possible negative real zeros a polynomial can have. So when I talk about real zeros, where do real zeros show up? X-intercepts on the graph. Okay. So if I were looking, like I've had these graphs up on all of our opening slides, if I were looking at these polynomial graphs over here, I'm focused on the x-intercepts, okay, at all of those graphs. And I'm looking for, like, how many... How many positive real zeros does this graph have? Top one? 2 positive real zeros. How many negative? 1 negative real zero. So it's like, do the zeros show up on the right side of the x-axis or do the zeros show up on the left side of the x-axis? Okay, so that's kind of like what we're looking at. And you could think like, you know, where Descartes' rule of sign is coming from, if you think about how we've been writing all of those polynomials, like when we take a positive real zero, we put it in as an x minus k. When it's a negative real zero, it ends up looking like x plus the number. And so depending on any combination of those that you may have, you're going to get some different things happening in your polynomial. So here's how Descartes' rule of signs works. We're going to start with positive real zeros. To find the number of possible positive real zeros in a polynomial, you're going to count the number of sign changes in the polynomial f of x. So that's like the regular polynomial. The number of possible positive real zeros is then equal to that number, the number of sign changes, or less than that by an even number. So count the sign changes. It either equals that number or it's less than that number by an even number.
So if it's like 4, it'll be 4 or 2.
4 or 2
Or 0.
or 0.
How do you know how to check?
Check what?
Check like whether it is a 4 or 0.
Oh, well that's just like remember, it's just the possible number.
Oh,
So we don't actually know which one it is until we find the zeros. Okay, but it'll at least narrow it down a little bit. Okay, so just so you can kind of, before we get into our actual examples, I've got a polynomial up here. So I just want to talk real quick about what I mean by sign changes. So I have f of x equals x to the 4th minus x cubed plus 2x plus 5. Okay. Each term has its own sign. What's the sign of the first term, x to the 4th?
Positive.
It's positive. So when the next term is negative x cubed, that counts as one sign change. So there's one. and then 2, and it stays the same, positive, positive. So we would say for positive real zeros, in this case, 2 or 0.
So let's say you had maybe it started with a negative x to the 4th. Would it be like from negative to negative, the 1 wouldn't count, and then there wouldn't really be any sign change between it, except for between the negative x to the 3rd and the positive 2x. That only count as 1. So you read it from right to left to make sure it's in order. Okay, that makes sense.
We had done some other examples. So, like, you guys had said, like, 4 or 2 or 0. What if there was 3 sign changes? 3 or less than that by an even number. 2 is less than 3 by 1, which is an odd number. By an even number. So then it would be 3 or 1. Would you put 0 on that list?
No.
No. 0 would be less than that by an odd number, right? So you could also have like 5 or 3 or 1. If you-
only with the evens, then?
0 is only with the evens because 0 is an even number. Okay. And so if you only had, like Lilith had described, a 1 sign change, then there was 1. And there's no other option. Right? Yeah, you want to have a negative number of real zeros. You either have real zeros or you don't. Yeah, you stop at 0. And if it's odd, number of sign changes, you stop at 1. Because 0 is not less than that by an even number. Okay? So, now that only does positive real zeros, but we want to know about like these zeros on the other side of the x-axis, right? The negative real zeros. So we have to change things up a little bit, okay? The rule is going to sound very similar, but there's one key difference. Am I close to that little x?
Less than by an odd number.
Which direction should I go?
Right.
There.
Good job.
Oh, negative.
Yep, negative sign. I don't know why this did that funny thing. So there's really 2 parts to Descartes' rule of signs. The part where you figure out how many possible positive real zeros you have, and then a second part where you find the possible number of negative real zeros that you have. So I highlighted in red the big difference. If you want to do the negative real zeros, you can't look at f of x because we use that for positive real zeros. So we have to look at f of negative x. And I'll show you that on the next slide when we do our first example, how we'll get f of negative x. But then the rule is the same. Once you find whatever f of negative x is, it's the same rule. Count up the number of sign changes from term to term. And then it's either equal to that number or less than that number by an even number. And these are like the only kinds of combinations you can have, right? Like 4, 2, or 0, 3 or 1, 5, 3 or 1, 1, 0, 2 or 0, 6, 4, 2 or 0, 9, 7, 5, 3 or 1, right? They can all kind of follow the same patterns.
So, because if you look at them backwards, it goes 0, 2, 4, and 1, 3, 5. So that just equals the odd and even numbers. So you could start hypothetically at like your number and just go by the pattern of whether or not it's odd or even, correct?
Yep. The difference between all odd numbers is an even number, and the difference between all even numbers is an even number.
Mine is 1.
Yes. Okay, so let's do an example on the board. Okay. Now, Descartes' rule of signs only talked about positive real and negative real zeros, but once we use his rule to determine that number of real zeros, we'll also be able to answer some questions about possible imaginary zeros. So we're going to add that in because we know about an imaginary solution. So we're going to determine the number of positive real, negative real, and imaginary zeros. And these are possible numbers. We might not know which one is right until we actually solve the final. Okay, so I'm going to start with the positive reals. And positive real is an easy one to do because you use the function that's given to you. So just look from term to term and like count your sign changes. 3x to the fourth is positive. And then we switch to a negative. So there's 1, 2, 3, 4. So we would have 4,
2,
0.
0.
Or 0. We don't know which one it is. We just know it's one of those. No, in the end you'll have 1 that is correct. 1 pair of all the numbers. Or 1 grouping of all the numbers. Okay, so negative real zeros. We can't use this same function. We've already counted all the sign changes. So we need to figure what f of negative x is.
So you got to make the x's negative.
Yeah. So like think just about like function notation. What if I asked you to do f of 2? You would plug 2 in for all of the x's, right? That's what function notation means. So if I asked you to do f of negative x, it just means what TJ said. Plug negative x in for all the x's. Now, when I plug negative x in, I'm going to protect it with a set of parentheses. Because I want to raise negative x to the exponent, not just x. Okay, so all the x's in those terms, I got to put in negatives. So I'm going to have 3 times negative x to the fourth minus 7 times negative x cubed plus negative x squared minus 13 times negative x plus 8. Everywhere I saw an x, I put a negative x. And protect it with a set of parentheses. The exponent is going to apply to all of negative x. Okay, so what we kind of want to do right now is like focus on patterns. If you take a negative x for that very first term, 3 times negative x to the fourth, and you raise negative x to the fourth power, you're taking negative x times negative x, which is positive, times negative x,
Negative.
which is negative, times negative x. So it goes back to positive, right? Okay. So if this is really just positive x to the fourth, then positive x to the fourth times 3 is still positive 3x to the fourth. Okay, so when I'm starting to simplify, the first term doesn't change. It's still 3x to the fourth. For the second term, negative 7 times negative x cubed, think about what happens when you do negative x cubed. It's going to stay negative, right? Negative x times negative x, positive, times negative x makes it negative. So if negative x cubed is negative x cubed, and it gets multiplied by negative 7, then it turns into plus 7x. So what's like a shortcut pattern we could use to decide what f of negative x looks like?
Even, it's going to be still negative. Odd is going to be negative. Odd is going to be even.
You could subtract 1 from
You
the
know.
highest number and then alternate. Would that work all the time?
What? Okay, so we want to focus on the patterns. What will happen when we do negative x and raise it to the second? It will be positive x squared, which it is plus a positive x squared, so it's going to stay positive, which it's keeping its sign. Okay, so here's what I want you to think about in terms of simplifying with the negative x's. If you're raising it to an even exponent, it will stay the same. 3x to the fourth and x squared haven't changed. If you're raising it to an odd exponent, that's going to introduce a negative, which is then going to change the sign of what it was originally. So this one turned into plus 7x cubed. What happens to negative 13 times negative x? It's plus 13x. And that's different than what it was in the original, right? What will happen to plus 8? It's going to stay the same. So some of you said like even is positive and odd is negative.
I get where you're going with that.
But I would just be really careful. It's like even it stays the same, odd it changes from the original.
It would be 3x to the fourth minus 7x to the third minus x squared.
Okay, but if it was minus x squared, then my rule would have been even stays the same. So it would have been negative x squared.
How would it stay the same though? Because it would be negative. I am at least. Or shoot, that didn't make sense.
Okay, let me finish this example and then we can look at another one, okay? But you want to kind of make it easier for yourself. So looking at the patterns is going to make it easier. But I would stay away from positives and negatives and think more about like keeps the sign, changes the sign.
So you said even it stays the same, then odd it just changes the sign.
Okay, now we have f of negative x. And we can count the sign changes in f of negative x. There are 0. So there are 0 negative real solutions. That's it. Right? Okay, do you remember at the top it said give the number of positive, negative, and imaginary? So we're going to make a little table. Positive, negative, imaginary.
There's no sign.
No sign changes in the terms.
It's always positive.
It was always positive. So you have to simplify the f of negative x first. Okay, what are our options for positive real zeros? 4, 2, or 0. So that means there's really like 4 possibilities right here. For negative real zeros, there's only one option, right? 0, 0, 0. If there were more than one option for negatives, like if it was like 2 or 0, I'd have to do 4, 2, or 0 with 0, and then I have to do 4, 2, or 0 with 2 negatives. I have to like do all the options.
Can I take a shot in the dark of what I think imaginary is going to be?
Well, let's just think about it together, okay? So that everybody knows where your answers are. You can think about it in your head and see if you're right. Okay. If I had 4 positive real zeros, and then I had negative 0 negative real zeros, how many imaginary zeros would I have?
-4.
4, 2, or 0.
Anybody want to back up their number?
0. -4. -8.
0.
0 because like the degree is 4, and so if you have 4 real ones, then you don't need.
The degree is 4 in that polynomial. So we're supposed to have 4 total solutions.
Oh, so 0 cubed.
And if there are 4 positive real solutions, there are no negative solutions.
So 0.
If there are 2 positive real solutions, 0 negative solutions, how many imaginary solutions are there? 2.
Oh, so just goes
Because her reasoning still works. The degree is 4, so there have to be 4 total zeros. Whether they're positive, negative, or imaginary, they have to add up to 4.
Oh, and the next one's 4.
And if I had no positive, no negative, then how many imaginaries do I have to have?
4.
4. Because the number of zeros has to add up to 4. Okay?
So if there's 0 negative, then pretty much positive, imaginary, just split.
Yeah. They have to add up to 4. Okay, let's try another one. See if you can use my like shortcut for simplifying f of negative x. I'm going to give you some time to think about it. Okay. So same directions, new polynomial. F of x equals x cubed plus 9x minus 25.
So there's one sign change.
problem?
Here we go.
It's like, since you see that in degree 3, and the only positive resolution we have is 1, there has to be 2 imaginary to make it 3.
What would be the choice?
Okay, remember to do the negative real zeros, you have to do f of negative x. So I'm going to do negative x cubed plus 9 times negative x minus 25. A shortcut that I can use here is whether or not the term will change signs. If it has an odd exponent, it will change signs. So this one will now be negative x cubed, this will be negative 9x, and this will be negative 25. So negative x cubed minus 9x minus 25. You might even be able to get away with writing f of negative x without having to do the substitution, right? Okay, so that would be nice if you could do that. Okay, how many sign changes in f of negative x?
0.
0 again, okay. Okay, so I'm going to do my positive, my negative, and my imaginary. So right now I have 1 positive, 0 negative. There's no additional options for those. So I only have 1 list. How many imaginary zeros must there be?
2.
Because the zeros have to add to the degree.
Will you always have an uneven number of imaginary numbers because you have to have plus or minus?
What a brilliant idea, Sierra. She said, will you always have an even number of imaginary zeros because you have to have plus or minus? Yeah, they come in pairs. So it only makes sense. You never have an odd number of imaginary zeros. Okay, now. In this one, they have to equal
Well, 3.
3.
But like this, so all 3 of them together have to equal the degree.
Yes.
Ah.
The rows have to add up to the degree.
That's
Lexi.
Does that mean if like the book says to find the imaginary zeros or the zeros, if you do, like if you just automatically know that you cancel out all negatives?
Yes. Okay, so that's where I was going to go with this. So we're doing this kind of at the end of the chapter as we're wrapping things up. You can use Descartes' rule of signs to work smarter, not harder, right? And like in pre-calculus in algebra 3, we teach Descartes' rule of signs earlier in the polynomials unit. You'll have seen it before. And then we ask students to try to use it to reduce the amount of things they check. So like if I came across this problem on a homework, on a quiz, or a test, I could first try to factor it, but it doesn't factor. So then my other option is my synthetic guess and check, but then I have to make a list of possible zeros. So I do my plus or minus p's over q, 1, 5, 25, which that narrowed down in synthetic guess and check. Instead of having to check negative infinity to infinity, now I have how many numbers on that list? 6, 3 positive and 3 negatives. But if you do Descartes' rule of signs, and you find out that the only possibility is 1 positive and 0 negative, what can you not check?
All negative numbers.
All the negative numbers. So now you've gone from infinitely many things to check to 6 to 3. Okay, so you would be then working smarter, not harder. I won't do any synthetics with negatives.
So for that, like,
They don't exist.
So you pretty much do 1
1, 5.
and then you have to do
Okay.
Yeah.
So it'd be like taking that as your big problem and then using synthetic games and you would like
Yeah. Okay, on your homework, and I think on your quiz and your test, like you just need to be focused about this positive, negative, imaginary table. Like you should be able to get the list.
Okay.
And remember, sometimes your list is longer, right? Like in this one,
Pretty low.
again, I would not check my negatives on my list, but I don't know if there are positives or not. So I don't have enough information to say they're all positive or they're are all imaginary. So it's kind of like that one, Descartes, like sometimes Descartes is super helpful, and then sometimes you're just like, could go either way. But at least we wouldn't check the negatives on that one either. Okay. Quinn, do you have a question or you just...
No, I'm just looking.
Okay. All right, so do you guys feel okay
Seems pretty easy.
if I let you
That's
go
just my
on
opinion.
homework?
Yo.
Okay, what's that?
Oh, it's so helpful, like that little trick.
Yeah. Okay, so you have two options right now.
That was.
You can work on the homework assignment at the top. That's on your gold sheet. It's 5 questions long, required problems. And then the other thing you could do is, if you had questions or issues on the page 202 assignment from last night, you get that out, get out a book, talk to people in your group, have a conversation. I can go over anything if we have questions. I am going to come around and pick that up. Or not pick that up, but look at it and check it for completion. So if you can get page 202 out anyway. And then you should also have your concept check. I want to pick up your concept check. So have that out at your desk. Even if you didn't make corrections, turn it in because I'll grade what you have.
Frank, I didn't make my corrections in different colors.
That's fine.